Hey there. Let's talk about the relationship between work and kinetic energy. We'll start by deriving the work-kinetic energy theorem. In doing so, we'll define what work and kinetic energy are. Then we'll do an application of this by working a physics problem involving a spring and mass system with and without friction. We'll start with Newton's second law. Sum of forces equals ma. We'll do this in one dimension, but it could be extrapolated to more dimensions. Well, mass times acceleration equals mass times the change in velocity with respect to time, dv dt. We can also use the chain rule to re-express dv dt as dv dx dx dt, which actually equals dv dx times the velocity, since velocity is dx dt. And we set that equal to the net work. And what we can do here is use separation of variables. We bring the dx over to the left side, so we have force times dx equals mv dv. To solve this, we integrate both sides. The integral of f dx goes from x0 to x final, and the integral of mv dv goes from v0 to v final. We've brought m out as a constant for our case here. The integral of f dx just goes to fx from x0 to x final, and the mv dv goes to 1/2 mv squared from v0 to v final. The term on the left is the work, F times the displacement. The term on the right we'll define as kinetic energy. Kinetic energy is defined as 1/2 mv squared, so 1/2 mv final squared minus v0 squared is the change in kinetic energy. In general, we may need to leave the force in the integral if it varies over x. The net work equals the change in kinetic energy is the work-kinetic energy theorem. Now let's look at an application. We have a box of mass m sliding across a frictionless floor at speed v0. Runs into a spring of constant k and compresses it until the box comes to a stop. How much work was done by the spring on the box? We'll use work net equals change in kinetic energy. We start by drawing our diagrams at two different times, when the box first touches the spring, still going at speed v0, and when the box has come to rest, completely compressing the spring. We've also expanded our expression for delta k to be 1/2 mv final squared minus 1/2 mv0 squared. We'll use the time 0 when the box first touches the spring and the final time to be when the box finishes compressing the spring. Our v final then is 0, and we've dropped that from our expression. This gives us work net equals negative 1/2 mv0 squared. We can also find out how far the spring was compressed. We've defined that delta x as x0 and x final from the second and third diagram. Would actually be that the work is negative 1/2 kx squared equals negative 1/2 mv0 squared. Here we've canceled the minus signs. We find the work done by the spring using the integral kx dx because the force of a spring is kx, which gives us 1/2 k delta x squared. We solve this expression for delta x to find the distance that the spring has been compressed. Delta x equals root m over k times v0. Let's do another problem. Here we have a box of mass m that's at rest with the spring compressed. The spring is compressed at distance delta x. The box is released, accelerating across the floor. Now we have friction between the blocks and the floor, characterized by mu k. The question is, how far does the box go from its rest position until it stops? We'll use the work-kinetic energy theorem to solve this. We could do this a couple of different ways. We could start when the spring is compressed, and then take another intermediate time when the spring is fully extended but the box is at its maximum velocity, and then a third time when the box is slowing down to when it stops. That's a little bit tricky because while the spring is decompressing, there's also friction acting on the box. A simpler method would be to just take T0 when the box is at rest against the compressed spring and T final when it's come to rest again. That gives us the work net as the work done by the spring plus the work done by friction equals 0, because delta K equals 0 if we do it like this. Starts from rest, ends at rest. Bringing the work done by friction to the right side, we have work done by the spring equals negative of the work done by friction. Remember, the work done by friction is force dotted with displacement, and that dot product actually gives us a factor of 180 degrees, so that gives us a factor of -1. Here we've substituted in that the frictional force equals mu k mg and solve for the displacement d. We have that the distance the box goes would be k delta x squared divided by 2 mu k mg. To recap, we've derived the work and kinetic energy theorem, defining work as the integral of F dotted with dx, and defining kinetic energy as 1/2 mv squared. We analyzed a couple of physics problems using work and kinetic energy theorem, a spring mass system without friction and another spring mass system with friction. Thank you very much for coming. Come again soon.